Web, they should be able to hear you.
Okay, oh, gotcha. Um, Our talk is going to be a little different today. I actually have note cards, which is an old-fashioned thing. And my talk is not going to be as good as the ones this morning. Those are all excellent talks. Don't expect that quality now. And my son, Joe, he's approved the script. He helped write it, and he approved it. My daughter, Arlie, back there, she saw it, and she said, "Dad, that looks good." My wife, Patty, didn't look at it. She looked at this shirt, and she said, "Where are your gray pants?" So that's what I did.
An important contribution.
Yeah, always take advice from the people who know what they're talking about. The first talk after lunch is always a bit of a problem. Because people, as you heard Rob ask, how did you do for lunch? A lot of people said great. And so that means you're probably going to go to sleep. But that's what I want, because earlier this year, I suffered a stroke. Before that, I suffered several temporal lobe seizures. Last year, Joe had to have emergency brain surgery, remove a lemon-sized growth out of his brain. Don't worry, we've all taken our pills, but it would be nice if you'd go to sleep and you won't catch my mistakes, because I'm going to make a lot of them, and I apologize for mistakes, but can't be helped. Let's see. I guess I push this button, right?
Just to be clear, that's not your fault.
Thank you.
Maybe I had a stroke. Now try pushing the button. There you go.
Hey.
Okay, and there's no hardware involved here. I'm not going to pass around any boards or anything like that, but I'm going to talk about these topics. Buoyancy, drag, turbulence. All three atmospheric topics. Has nothing to do with your payload, but it directs it, slows it down, or speeds it up, whatever. And then I'm going to talk about the processing technique that we use to get accurate and high-resolution ascent rates. Then I'm going to talk about 12 balloon ascents, 5 from EOSS, and then 7 from other people, including a Pico balloon that was talked about earlier this morning, launched from Hamvention. I'm going to show you the ascent rate for that. Buoyancy. First, I want to talk about buoyancy. And some people in here may think that hydrogen takes your balloon up. That's not true, because hydrogen doesn't know which way is up. Hydrogen knows which way is out. It pushes out on the balloon equally in all directions. The atmosphere, though, does know which way is up. And on the bottom half of your balloon, it pushes up more than it pushes down on the top half. And that's what makes the balloon go up. And that's one way to look at buoyancy. Another way that we'll look at in just a bit is hot air rises, cold air sinks. We're going to look at that on a global scale. Next is drag. Once your balloon is going up, the atmosphere starts to drag. This is a plot of drag over here, drag coefficient, more drag at the top, less at the bottom, and a thing called Reynolds number along here at the bottom. And Reynolds number is the force required to push a balloon through a fluid, divided by the force to pull the balloon through the fluid. And note here, 7 decades covers a big range. Balloons are up on this side. Down over here are like a bowling ball dropping through honey. That's a low Reynolds number. Another low Reynolds number is a coronavirus moving through the air in this room. And if any of you see one, let me know. We'll get Rob to get it right out of here. But that's down here, and that's not what we're talking about when we're talking about balloons. We're talking about up here. Now, it doesn't take much algebra to go from this equation to this expression for Reynolds number, which is atmospheric density, rho, velocity, ascent rate in this case, and d diameter of your balloon, divided by atmospheric viscosity. And that's what is plotted here for a sphere. No, this is only for a sphere. And what's going to happen tomorrow for EOSS's balloon, it's going to start out and maybe go right here. Now let's look at that and note down here, viscosity in the atmosphere doesn't change much. Density in the atmosphere decreases as you go up, but it's not fast. And you all know that the diameter of your balloon increases as you go up, but it's not fast. So the only thing fast down here is velocity. So you can think of this, now for fast changes, you can think of this as the velocity axis. Okay, suppose you go right here, and then you get a little fast impulse of velocity. Your drag goes down, which causes fast increase of velocity, which makes drag go down, fast increase of velocity. That's positive feedback. Which is, the whole system, the whole balloon system is unstable right here. And it will work as hard as it can to get out of there. And tomorrow, what will happen to the EOSS balloon, like it's done for almost all of our flights, it'll keep going down here, go around here, and come out here. And then an increase in velocity will cause an increase in drag, which will cause a decrease in velocity. Stable operation. And all 5 of the examples I showed, the results, you'll see that happen. When it's out here, turbulent flow around the balloon. And not much drag. In fact, it drops by about a factor of 4. So low drag, and that's where EOS's balloon will start tomorrow. Low drag, and then as it goes up, the density goes down. Pretty soon this decreases, goes around here, unstable, it goes up here, right to here. So these are the two places that it'll operate stably. And up here, the flow around the balloon is laminar. And in all of the EOSS results I show, you'll see this transition, and I call that the Reynolds number breakpoint. It goes from down here very quickly up to here, because it doesn't last very long in there. And of course, you can't end something like this without talking about a golf ball. Golf ball's a sphere. It has a Reynolds number drag chart, something like this. The big difference is that this structure is about 10, a factor of 10 lower. So instead of 300,000, it's 30,000. And that's why golf balls, that's why they use them. They put dimples in them so they go further. And I checked to make sure I covered everything, and yes. Now, the second one, or my next slide, I'm going to talk about turbulence. And you might all say, well, where does turbulence come from? Okay, here's where we all live. Here's the Earth. This is the atmosphere. And where the energy comes from for turbulence is the sun shines straight down at the equator and grazing at the poles. That's why the equator is colder than the poles. And that causes the heat at the equator, causes the hot air to rise. That's buoyancy. The hot air rises. And it sets up these big, big convection cells. Rise up, go north to about 30 degrees. This is the equator. This is about 30 degrees. And it comes down back like this. Around the equator, because of this effect, rotation of the Earth, you see the trade winds. These red arrows are the trade winds. You also see up here, where we live, generally weather moves west to east, generally. And generally our balloons go west to east. Now tomorrow that isn't going to happen. And a thought experiment for you all is to think about this, and you'll see why partially, not the entire reason, why partially we're going to have to drive out to Lyman tomorrow. It has to do with this very picture. And moving on, those big convection cells, they're called Hadley cells, that on the previous slide, this type of overturning, they keep turning and they break down. They get smaller, they never get larger, they break down, they reorient themselves and keep getting smaller and smaller. And that's where the mean flow comes in at about the outer scale of turbulence, about 2 to 5 kilometers. And you have eddies that form. Big eddies, and then they break down to smaller eddies, and they continue to break down. Energy is flowing in this direction. They get down to real small eddies at about the inner scale of turbulence. And that energy is dissipated in heat by viscosity. Real little. And this, of course, here's 2 dimensions. And it's much more complicated in 3 dimensions, as you would think. And I've always found when things get complicated, it's best to look at them another way. And in this case, poetry does a great job. Here is a great little poem. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls and so on to viscosity. And it explains it all. This is written, this poem, by Lewis Richardson in a book, published in 1922. Way, way ahead of its time. Because the title of the book is Weather Prediction by Numerical Process. Decades before computers were even invented. And Lewis Richardson set down the basic rules for weather prediction 30 years before computers were invented. He did live till 1953, and he did get to see the first numerical weather prediction, which was done in 1951 on the UNIVAC computer. And so he got to see his ideas put into practice, but he was way ahead of his time. So there I've covered those first three things I was going to talk about. Now I'm going to talk about, I think, our problem. Problem all of you have, all of us balloon people have when we try to predict ascent rate. We get time coming down this way. We get samples of height, and in our case, GPS height, which has some noise in it. GPS height measurements are not as good as horizontal measurements. They have a lot more noise. And so we calculate velocity, height difference divided by time difference, feet per minute. And so we calculate that coming down for each of the time units. Over here, we have just a little algebra to go over here. And then we're going to average. When you have any noise, first thing you want to do is average. So let's average this column. Well, look at this. This cancels with that. This cancels with that. This cancels with that, and so on. Your average velocity, you throw away all your data. You throw away, to get an average velocity, you only use the first and last term. You throw away everything else. You don't want to do that. That's the problem we're going to talk about. I hope, if I can, let's see. And now I'm going to talk a bit about how, in our case, we got around this problem. Imagine that this is GPS height, up and down. These are measurements from packets. In this case, 16 packets. And you can see pretty noisy. And there is an algorithm, and I'll bet everyone in this room has this algorithm. Linear least squares algorithm. If you have a spreadsheet, this almost certainly is built into it. And so you all have this, and what this algorithm does, it takes, in this case, 16 noisy samples, and it makes the best fit straight line. The slope of that line is the velocity. So what this algorithm does, takes 16 noisy measurements, gives you one much better measurement. And let's see if I've lost anything here. I'm at slide 8. No, I haven't lost anything yet. Good. Now, this is available anywhere. here's the thing that we did. Now, imagine that's a point, we're interested in that point, and that our 16 samples or some other number, like I'm going to be looking at averages of, let's see, I think 5 samples to 20 samples. So somewhere in there, there's 5 to 20 samples. And this is the straight line we got out of the algorithm. Below that point and above that point, note curving down. So during that time, your ascent rate decelerated. And if you look at it on the graph, it's curving down on the profile. It'll be curving down. I encode those red. On the next slide, you'll see what I mean. This, on the other hand, if it curves up like that, these are 16 points, straight line, and that's greater. That's acceleration, and that's curving up. I encode that green. And so these are scaled accelerations, difference in velocities, difference in slopes, and I found out that you had to divide by standard deviation of over here, standard deviation there. So I divide by, both of these are positive numbers, they're added together. So this is a positive number that scales. And what it does, if it's noisy, it makes your scaled acceleration less. When it's not noisy, it makes it better. And you'll see what happens for that. Okay, remember, red curving down, decelerating, green curving up. Now here is an EOSS flight from last November. Here is green. This is the green I'm talking about. This is the red. And this colored area is a straight line. And you can see curving up, green, through here. And if you look really closely right here, you can see red curving down, and so on. Remember EOSS, our flights? This is turbulent flow, low drag. And you can see the Reynolds number breakpoint, which is right about there. It changes. It's the peak of deceleration, the biggest deceleration, the whole flight. And you can actually see that, and maybe you can't out there, but here I can look up and I can see, yep, that whole average slope is much more, not much, is more than that. So it's slowing down, and this is laminar flow in here. And the descent. Now, remember this is acceleration that's scaled. If you integrate acceleration, you get velocity. And that's this blue line. The integral, and integral means area under the curve. So you take this curve, let these red things be negative, and take the area under that curve, you get this blue curve, which is acceleration. And you have to unscale it, and you have to put in a constant of integration. Up in that corner, you see the raw data, that is 1 minute spacing. I should have pointed out that our EOSS flights are all 30 seconds per packet. So the raw velocity data are the red points. Blue velocity data are the integral of this, and then you adjust that. There's two numbers you have to adjust. One is general scale, and one is constant of integration. Get an RMS difference of 132 feet per minute, which is the smallest I could get. And then that's the ascent rate. And as you can see, if you looked at just at the raw data, you see a lot of noise in the upper part. But this is a much better picture, much better estimate of velocity. Now I have 3 more USS flights. These are all from last year, before my stroke. So I put more effort into the visualization. After the stroke, you can't do it anymore, so you just put less. You'll see that. But these first 4 are all from last year. This was from last November. And this is a 3,000 gram balloon with student payloads and from Littleton schools. On the same day, we launched another one from Metro State. And this one didn't go quite as high, only went to 70,000 feet. But you see some similarities. A lot of green down here, peak in red where Reynolds number breakpoint is. It's about at the same point. Now let me go back and forth here. About at, say, 65,000. These dots are 30 seconds apart. Right there is the biggest spacing. That would be that point right there. About 65,000. Let's see. Whoops. And about 65,000 there. So very similar flights. Same day, same atmosphere, almost the same time. Same size balloons, nearly equally loaded. And you see, similarly, the upper part is a lot more noisy than the lower part. Another thing that Larry always does, puts in enough gas to get above 1,000 feet per minute. You're going to do that this time, right? And so all of our flights, all the USS flights, start out above 1,000 feet per minute and come down. Some not always go below 1,000, but get near 1,000. But they have the same general feature. 1 week later, we did this flight. Less averaging. We're now averaging 3.5 minutes, which is 7 points rather than 10. And you see a lot more structure here, a lot more noise. That's because we're not averaging as much. And you can see the atmosphere, or at least our estimate, more of the small scale turbulence gets through because we're not averaging over as much. And this one is interesting because look at the peak here. Those others, the peak was just about this high. This high, the peak, the maximum deceleration, very high, very narrow. Look it up there, you can see why. The first part of the flight is all of the raw data is up. The second part of the flight, it's all dropped. In other words, there was a very sharp Reynolds number breakpoint, and I'm sure you can see it from out there. More slope here, less up there. And in this case, it happened to be at about 50,000. Okay, so that's,
Hey, Russ, go back, can you go back one slide?
I hope,
Yeah. Yeah. Well, maybe not. Anyway, some of those flights, it looked like there's a pretty sharp deceleration around the 45,000 foot level.
That-
Not this one, but.
oh yes, deceleration.
Well, there it is. I didn't look at this. Yeah.
Yeah, oh yes.
So what's going on in that first,
Right here?
no, right at 45,000, because you're always saying that there's a
Oh, it
break
is?
point at 60,000.
Well, most of ours do that. This one did not.
Okay.
There, and it depends on how Larry fills the balloon.
Oh, it's Larry?
Yeah, this one.
So we're gonna blame the gas pass.
Yeah, yeah. See, it's lower, closer to 1,000. Larry is sometimes above 1,000, quite a bit.
So
So,
I have a question that relates to this, so I was gonna ask later. So you were doing stuff on a sphere. Now, what actually happens, we're more egg-shaped. So that's gonna make the laminar flow start at a lower elevation because of the shape change.
yep,
Isn't that correct?
that's correct. The approximate.
So if he fills it with less, it's gonna be more egg-shaped than if he fills it with more, keeps it tighter and more of a sphere than what I thought in the past.
That could be. I'll let you think about it. And that's code for I don't know.
Well said.
Russ, repeat what he asked.
Oh, yeah. He asked what's going on here? Why are things different? And does it have to do with the shape of the balloon? See, the drag picture I showed you, remember when I talked about the golf ball? That assumes a sphere, perfect sphere. Balloons are not. When they get up high, they are real high. When they're down lower, they're more upside down teardrop shaped. And George asked, why is that? And I cleverly said, think about it. But then I admitted, I don't know. Okay, now everything is this year, 2024. This is a flight in Nevada. 1 second data, or I mean 1 minute data, and I'm doing 10 averages, so this is 10-minute average, and you can see my algorithm for determining the Reynolds number breakpoint. Pick this number, and there is some indication of that here, but something funny is going on. And if you look here, remember this line is straight, the green line, that you can see increasing all the way, so lots of green here and not much red. And that means slowly increasing, going up. And remember, this is with 10-minute averaging. And on this flight, I actually changed the averaging. So I'm going to double go to 20-minute averaging and then to 5-minute averaging. And you'll see the difference in this ascent rate plot. This is 10 minutes from the previous. When you go to 5 minutes, you see a lot more of that small scale turbulence. Remember, big whirls have little whirls, and you see the little whirls. Out here at 20-minute averaging, you see very little of that. And I am not sure what's going on here. Because this, it probably is not a Reynolds number breakpoint, even though my algorithm found it. But it does, it's not nearly up to 1,000 feet per minute.
Now, is
But
that a different size balloon?
I don't know.
I'm just looking at the ascent rates are quite lower, much
Yeah.
lower.
This is, several of my plots, I don't know anything about the balloon. I would suppose this was a guy out in northwest Nevada, probably launching a 1,000-gram balloon, smaller, with a single payload. And now, moving to radiosondes, I'm going to talk about 3 radiosondes launched from Fort Collins, CSU, probably, and right at the end of the school year, probably some type of research project by students. And Jeff, N2XGL, receives those packets at his house, puts them on the internet, and I get the data and can actually analyze them. Now, the interesting thing is they're launched about 10 days apart. The first and the last ones follow about the same track and some similar things. They're kind of similar. Launch from Fort Collins, which is where CSU is, and ending up out here near Briggsdale. And first one, 10 days later, here's the second one. About the same thing. A little different, but about the same thing. Let's see. This is my plot of the first one, where there really was a Reynolds number breakpoint down low. Remember, it starts up here at about 13,000. So this is a real Reynolds number breakpoint, but this is only averaging 2.5 minutes. Oh, and I should have pointed out, I forgot to point out, excuse me, since the new year, I also look at things for the descent, and it's usually all green. The balloon is curving up, moving down, but curving up. So this is green. This has a little red at the end, so at the end, it's starting to go down for some reason. Usually, they stay green all the way. Then, this is the last one of the 3, and it's kind of similar. It's got not quite as much initial velocity, and not as it has more averaging, so a smoother ascent rate. A little red at the start, which you can kind of see there, but then mostly green. But now this middle one, which was the first thing you notice is the difference. Remember, the 2 previous ones went from Fort Collins to Briggsdale. This one, which is in between, comes way down here. And if you look here, you see no descent, post-burst chaos. They lost something on when the burst happened, and they never saw anything after that. And look at the very large excursions in the ascent rate down here alone and up high. Did that cause the post-burst, the failure at post-burst chaos? Don't know. But you can see all the structure. You can even see this, all the small scale turbulence in just the height. See how these, and you see lots of red alternating with green, up and down, red, green, and so forth all along here. And that's what shows, doesn't generate, it shows all of this small scale turbulence below about 50,000 feet. And this became kind of interesting, so I looked at it this way. And you can see the raw data, which is different heights, goes even to 0 here and almost 800 up there within just maybe 10 or 20 seconds. And if I am able to adjust this to get 61 feet per minute RMS difference, which is really good. It shows that the raw data shows that the turbulence is really there, even in the raw data. And we just smoothed it out a bit. But this is one of the most interesting ones that we have found. And this is just completing the first one, which was the first part of, or the very first one, and the very last one. Or no, this is the first one, and the previous one is the last one.
Russ, have you been able to correlate any of these real, lots of differences in ascent and descent rates with any indication of atmospheric instability?
Yeah. But I do know it's really there, but, and it's turbulence, it's turning and existing, but no, I haven't found anything that I could say, here it is. And now, our last EOSS flight, EOSS 360. And this is just classic flight, everything almost perfect. I mean, Larry did his job just great. I did average a little longer. I averaged for 14 samples, so this is 7-minute averaging. You see, green, and then kind of alternating. Reynolds number breakpoint right there, which is about 65,000, right in there. And descent, all green, so things are working okay in the parachute. And
I don't know how to turn it off.
Step on it. A couple water work, yeah.
now, so this is just a perfect flight. And it had an ADS-B on it. And here you see it launching from, this is our Deer Trail launch site, coming down near Akron. And here's the height curve. And if a sharp-eyed person will see there's a little difference. The reason is ADS-B is pressure height, not GPS height. So this is this breakpoint, which you can kind of see, is a little lower. That's because it's pressure height. And you can see horizontal noise. And this is horizontal. The yellow line is horizontal. You see noise. Now, is that noise, this is Both of these our APRS tracker and our ADS-B tracker, same flight string. These have to be related somehow. I don't know how. I do know that horizontal measurements, GPS, are about twice as good as vertical measurements. So some clever person could analyze this and use this to improve the height measurement and use the height measurement to improve the horizontal measurement. So let's see. And then on this very same day, May 18th, WVI-12 was launched from Dayton. And this went around the world, you say twice. I only caught it.
Almost 1.99.
Okay, but it did come over Boulder.
Yes.
And
Right.
I saw it and I said, gee, maybe I'd like to look at the launch of that. And I used all the same software, same procedures. And this is the plot I got. Now, this isn't a Reynolds number breakpoint. This is going into float.
Right.
And maximum deceleration as you go into float. And this is not turbulence like our EOSS flights, turbulent airflow. This is laminar airflow. And I'm sure of that because the ascent rate's so small, between 200 to 300. And it goes up to about 40,000 feet, and you can see it here, up at about 40,000 feet, just below. And my algorithm, the peak point has what it would have called burst. Of course, no burst, but it went the peak point is right here, and that's why the analysis stops there. And there's a little fluctuation, and you can see that down here, and going up and coming back down, and so forth. And so now another one. This was one launched from Las Cruces just a couple of weeks ago, Las Cruces Airport. And it has Reynolds number breakpoint, and clearly here. But what's so interesting about this one is the descent is mostly red. In other words, curving down, not curving up, but moving down, curving down, red, and a little bit of curving up here, and red here, curving down. So this guy, KD2 UJJ, is doing something to get rid of post-burst chaos. Don't know what, but clearly he has changed the structure of his descent by some way. And now I have the last one, which I think is the most interesting.
It kind of looks like on that previous slide, that's probably a Pico balloon since it's only going to 25,000 feet. And that's probably a balloon that's leaked. So you're coming down with the balloon still attached. And it's just slowly leaking.
Could be. Good point. Good point. Good point. I hadn't thought of that it could be a failed Pico float. And this final one, launched from south of Albuquerque, is quite interesting. And it's another nearly floater, but not, it doesn't go into a perfect float. There's still some vertical ascent in the upper part. This is a 10-hour flight, so lots going on. But of course, the question is, what happened at these two places and at these two places. Now, my velocity measurement shows them both up there. See the two loops? One down, the two down lower, the two up higher, with a big space in between, with around zero.
I believe that's a solar balloon. He launches solar balloons. There's
But
two-
it didn't go down at night.
Oh, it did?
It didn't go down at night. I thought his name is Anderson, I think. And he takes balloons, rubber balloons, fills them with soot, black soot. And I really mean soot. And then he sets them out on a sunny day in right south of Albuquerque. The sun heats them up, and they go up to,
About that elevator.
yeah. And he's done that several times. But the question I have, I was hoping he would be here. Because it's not far from Albuquerque to drive here. Certainly you guys from New York, we came further than that. But how did he do that? I don't know. I don't know. So I do suspect that these two blips in the middle, small blips, are where he tried to do it and it didn't work. I don't know that though. Anyway, that's the last of my. Does anyone have any thoughts on this? This is.
That might be a vented balloon. He tried to vent it several times to level off. So there's probably maybe some active venting if that's not a solar balloon.
Or even like a passive mechanical vent that has a little hysteresis to it, where it opened and kind of overvented a little so you go down, and then more heated came starting to come back up.
So, anyway, we've talked about buoyancy, and remember I said hydrogen doesn't know up from down, and that's true. We talked about drag. The Reynolds number is always high for balloons. We talked about turbulence and so on to viscosity. Put those 5 words into Google. You'll find out the rest of the poem, everything about Mr. Richardson, and the book he wrote, that incredible book. And you'll also find something about Richardson's number, which is somewhat like Reynolds' number, except for Richardson's numbers for turbulence. And I talked to the processing and 12 balloon ascents. Any questions?
So Russ, when you talk about GPS height noise, do we get a number? Is that like n number of feet? Is it a random number? Is it, when I look at noise from my end of the world, it's like pink noise, right? Or white noise, where we've got some sort of a noise source. But when you talk about GPS height noise, I'm assuming you're talking about variability between GPS measurements, right?
That's correct. And in our case, EOSS's case, they're 30 seconds apart.
Well, we also have 2 sets of those that go off. So we always have, there's an upper and a lower, right?
Oh,
We
yeah.
get 2 sets of data. And if we sit there and look at it, we can see that sometimes there's a significant amount of variability between those 2 numbers, even though they're roughly 15 seconds apart, right? Because they're spaced to be they're time slotted to be halfway between each other. Is this a problem with how we're measuring the GPS data? Or
Oh,
is it
no,
intrinsic to
this
the
is
system?
This is in the system. And the name is VDOP, Vertical Dilution of Precision.
Hang on.
And compare that with horizontal, HDOP, Horizontal Dilution of Precision. You'll see that VDOP, there's more, that your horizontal measurement is about twice as good as your vertical measurement. Still not perfect. I mean, there's still noise.
So it's vertical dilution of precision.
VDOP.
Okay. On that lovely picture of the Earth with all the convection stuff, it looked like the atmosphere was wider at the equator than it is at the poles. So it's bigger this way.
Yep, because, and if you look at the tropopause is the boundary between the troposphere and the stratosphere. And if you look at data from the tropics, it's high and very clear, no question where the tropopause is. If you look at data from the poles, it's much lower and really hard to find. And that's because of the way the atmosphere is shaped. It's not, the atmosphere is more shaped, there's more atmosphere at the equator, more air at the equator than at the poles.
When you look at descent rates,
Descent or?
descent rates and the,
If somebody had Mike and Mike.
hey, Mike, you got that mic? Hang on. I gotta, no, wait, I gotta go down to get Mike, because now we have 3 mics. So,
Turn it on.
what was it?
Yeah.
There's an ON switch.
What does that do?
I don't know.
If I
If
have to
it
show you.
starts ticking, I'm throwing it. Tasting the microphone? Okay. Descent rate and that, yeah, here, just right there, right on the forehead. We've flown all kinds of crazy descent rates based on a whole bunch of different parachutes, right?
Right.
And have you seen any difference when we drop payloads faster versus when they take a more leisurely ride down in terms of how that data looks? You know, you've got that descent curve, right? And then you've got the red and the green stuff underneath it. If we drop payloads faster, does that change the red and the green portion of that curve?
If we drop them faster, it will be a higher green curve. It will be moved up, but our descents, EOSS, we hardly ever see any red on the descents because our parachutes fill up, and as they come down into the denser atmosphere, they slow everything down. And we hardly ever see, now of course, as you know, when we've had failures and they come down really fast, we've had a few of those. But
Well, Russ, I'd like to tell you, I felt like Beaker from the Muppets. Okay? And my hair was standing up, smoke was coming out of my ears, my eyes were glowing. It was brilliant stuff. I understood about a tenth of it. Thank you.
well, I'm sure you've got more than that. Any other questions?
Just a quick comment, and my recent obsession has been chasing these, radio songs that the Weather Service launches, and they beacon GPS data once per second, and that allows you to see some very interesting things.
Yeah.
You can see the pendulum effect.
Mhm.
Usually there's about 60 feet of strength between this and the neck of the balloon, and I haven't seen what you presented. Now that I know to look for it, I'm sure I'll see it, but you can see some really interesting things with that much data. With 30 seconds between packets, you kind of run into a Nyquist dilemma. There's just not enough sampling to really, see the whole picture. But I don't know, this is very interesting, and I'll definitely be looking into it further. But on the descent rate, I can always predict how much of the balloon is going to be left based on the descent rate. If it starts out, or if I see, average of 5 meters a second, there's going to be a lot of balloon. If I see, 2.3 meters a second descent, there's just going to be a little bit of neck. So it's interesting to start correlating that and figure out what type of landing it is and all that. This is very interesting. Very good talk.
Good point.
We actually have 1 second unit that we go on, in situ in the local.
Yeah.
So, we have that available for the last 100 and some odd flights. So if somebody wanted to go to 30x precision, we'll make sure it's available.
And the reason I don't do that, that takes a lot more work to deal with that much, a lot more work. The 30-second data is, I can handle that.
Yeah.
That's what computers are for.
But I'm very curious what correlates, what that event is. Does the balloon change shape, And it sounds like we just haven't figured that out yet.
Yeah, one of the big things is, previous to this, there was always lots of noise on the data. And what I'm trying to do is make less noise on the data so we can see these effects, like turbulence, like the drag thing. And that's, and on names that everyone here will probably know. I used to, when I first joined EOSS, Merle McCaslin, who names you know, Mike Manus, they were, and I would be with them at the ground station, and Merle would say to Mike, what's the ascent rate? And Mike would tell him, but in whatever it was. But it became clear that this ascent rate changed all the time. And so Mike should have been telling Merle, about every minute what the ascent rate was. But just once or twice, and Merle would be satisfied with that. But there's a lot more going on than just one number for ascent rate.